today we're going to start 9.1. Chapter 9 is all about vectors. And we are splitting 9.1 up into 3 days. Okay, so today's going to be a lot of terminology. And then the next 2 days we're going to get into applications, which means a lot of fun story problems for you.
Why is homework such a problem? That's kind of many.
Okay, so today what we're going to do is we're going to find the magnitude of vectors and then perform basic operations with vectors. Now, if you're in physics, and will you just raise your hand real quick if you are in physics? Okay, you're going to see some overlap between what you do in there and then what you do in here. Some of the methods might be different, but you can use your own method to solve as long as you're showing your steps. So the first thing we're talking about is called a scalar. So this is a quantity that's just determined completely by the magnitude. For instance, a length that's 5 inches, okay, then that would be something that's scalar. Okay, the length is represented solely by that number and that quantity. Same thing with a mass, 1 kilogram, an area, I gave you 4 feet squared, a temperature, 36 degrees Fahrenheit, or energy, which is 60 joules. Those are all scalars because they're represented only by their magnitude. Vectors are different. They are going to not only be represented by their magnitude, but also their direction. Okay, so we describe the displacement, which is going to be really just the position of your vector. And to describe the velocity of a moving object, you're going to specify both the speed and the direction. So there's several quantities that are going to have magnitude and direction, and some of those are displacement, velocity, acceleration, and force. And then we're going to use vectors to represent those quantities mathematically. So a vector in the plane is just a line segment with an assigned direction. I'm going to let you copy that part down. In your textbook, you're going to see are labeled in bold. We obviously don't write in bold, so what we're going to do is we're going to write the symbol for the vector, which is the same as the symbol for array, if you remember back to geometry. Okay, so you're going to have that arrow. So this could be called U or AB. So here's your terminal point. That's where it ends. Your initial point is going to be where it starts. And notice here that it says the length of the segment AB is called the magnitude, or it could be called the length of the vector. Okay, so the magnitude is going to be a formula that you are familiar seeing, and we're going to get to that in a little bit. give you time to write that one down, and then we're going to go over that as well. Okay, so the magnitude is the same thing as the length. The two vectors are equal if they have the same magnitude and are also going the same direction. So when we represent a vector, we have two components, A and B. You can see it kind of looks like a point, but instead of soft or hard brackets, we have these carets, okay? Or you can think of them as arrow brackets. Your A value is what is the horizontal component. Okay, so the A is the horizontal, the B is the vertical, which makes sense because this is in the same position that X would be, and X is the horizontal axis, and Y is the vertical axis. Okay, so a vector is going to represent magnitude and a direction, which is going to be a particular arrow in the plane. But when you have the vector AB, it has many different representations. Okay, all of those are dependent on the initial point. So I can give you a vector 3, 5. The horizontal component can be 3, the vertical component can be 5, but it can be placed anywhere in the plane depending on where your initial point is. Okay, so what I asked you to think about is how is that different, the vector, from the point AB? Okay, so we just talked about how the vector can be placed anywhere. If I told you to draw the vector 3, 5, I could have 30 different representations. Okay, if I asked you to plot the point 3, 5, how many representations is that going to have? Just one. There's only one place where you can plot that point in the coordinate grid. Okay, so the vector has many different representations. The point is only going to have one. All right, and then let's go to the next page. So the next page, the first thing we're going to talk about is component form, bless you, of your vector. And component form your component form is going to be made from an initial point and a terminal point, and then you can go ahead and calculate what the vector is by subtracting. So notice this is x2 minus x1, so it's the terminal point minus the initial point. Okay, so it's the terminal point minus the initial point, which is going to give you the vector. Okay, so the vector is equal to the terminal point minus the initial point. Okay, and then of course you have your components with that. So for example 1, you need to express the vector with an initial point P and terminal point Q in component form. Okay, and that just means in terms of A and B. Okay, so that's the vector that we're going to try to find. Now, there's a few different ways you can do that. You can use your equation, or this one is on the graph. So it's actually going to be very simple to count the horizontal distance and the vertical distance, right? If I'm looking at this from a horizontal distance, to get from P to Q, I'm going over how many units? 5, right? 1, 2, 3, 4, 5. So I'm going left 5. So if you're going left 5, you could represent that as a negative 5. To get to Q, from P, I'm also going up. I'm going up how many units? I'm going up 3 units, right? You can count that and see, right? You're 1, 2, 3. Okay, so if you're going up 3, that's going to be a positive 3. Okay, so your vector in component form is just going to be negative 5, 3. So if you're going left, it's negative. If you're going right, it's positive. If you're going up, it's positive. If you're going down, it's negative. Now you could also use your points. So you know that your initial point P is 2, 1. And then you know that Q is negative 3, 4. So you could also just subtract those, right? You could also find V by doing x2, which is negative 3 minus 2, and then 4 minus 1. And again, that would lead you to negative 5, 3. Okay, you can use similar strategies for B. Like when you look at this, okay, if you are going from 2 to 5, what's your horizontal distance? 3. Okay, from negative 1 to 4, what's your vertical distance? What's your vertical distance? 5. Okay, now again, you could also find that by subtracting. Okay, so you could do 5 minus 2, and then 4 minus negative 1. Okay, so either way you could get that. Alright, now what we're going to do is we are going to graph them. So it says to sketch the given vector with the initial point 4, 3, and find the terminal point. Okay, so before we graph, I recommend finding what your terminal point is. One way that you can think of this is that you know when you do x2 minus x1, that's going to give you your horizontal component, which is 4. Right? If I were to do the terminal point minus the initial point, wouldn't I get the horizontal part of the vector? Right? And I already know my initial point, which means I know my x1, y1. So if I were to substitute in 4, I'd have x2 minus 4 is equal to 4. And then what would I do to both sides to get x sub 2? Add 4. So then my x sub 2 would be 8. That would be the horizontal component. Then to find the vertical component, y2 minus y1 would be negative 3. Well, I know that my y1 is 3. So then I would add 3 to both sides. Negative 3 plus 3 would give me 0. Okay, so then your terminal point, and this is a point, so it's not going to have the carets, it's going to be the soft brackets, would be 8, 0. Now let's look and see what I just did there. See how I ended up adding 4 and adding 3? Okay, the significance of adding 4 and adding 3 is that 4 and 3 is what? Your initial point. Okay, so essentially you can just add those together. So if you have 4 plus 4, that's going to give you 8. If you do negative 3 plus 3, that's going to give you 0. So now that I know my terminal point, I can set up my scale. So on my graph, I'm going to want my scale to go by what? 2's. Okay, so this will be 2, 4, 6, 8. Now with my y-axis, I can just go by ones. 1, 2, 3. Alright, so then I'm going to go ahead and plot my terminal point and my initial point. So my initial point is 4, 3, so 2, 4, 1, 2, 3. And then my terminal point is 8, 0. So then I'm going to connect these. And when you draw your arrow, you don't want it to be above the point. Okay, it's pointing at the terminal point. And then you're going to label that as your vector u. Okay, and you're labeling it as u because that's what it's given as, u. Okay, so when we do B, let's try to do the shortcut, right? So before, we found that you could just add the 4 and the 4 to get the 8. So here, if I add 4 and if I add 3, that should give me my terminal point. So negative 8 plus 4 is going to be negative 8 plus 4 is going to be negative 4. And negative 1 plus 3 will be 2. Okay, so here's my terminal point. Now you can double check and make sure that this matches by counting the distance. See how I'm going down 1, 2, 3 here, and negative 3 was that part of my vector, the vertical. And then my horizontal was 2, 4. Okay, so then that matches my horizontal. So that's how you can also check it when you graph. Okay, this one I only have to go by ones. This would be 2, 4, and did I say 2s or 1s? Yeah, good. Okay. Okay, so you just have to go by 1s. So my first point, 4, 3, is here, and then I have negative 1, 2, 3, 4, 1, 2. Okay, and then I'm going to draw my vector. Bless you. Alright, and then this one is also called U, so I'm going to label that. Okay, and then again you can check to make sure that the span is going to be 8 to the left. So here's my point. 1, 2, 3, 4, 5, 6, 7, 8. And then I'm going down 2. Okay, and you're going down 1 because you have negative 1. Okay, and then you're going 1, and then that was your over 8. Okay, so down 1, left 8. What questions do you guys have for me on that? I know it's a lot of terminology. Okay, so the next thing we're going to talk about are some geometric descriptions. Okay, and in particular, we're going to start with the addition of vectors. So if you have the displacement as a vector, AB, if that's followed by the displacement of the vector V, which we're going to call BC, then the resulting displacement is AC, and then it says as shown above, but it's not shown above yet, so we have to create that. Alright, so what we're going to do is we're going to go ahead and create a vector AB. Okay, your AB doesn't have to look exactly like mine. Okay, but this is my vector. Okay, starts with A, ends with B. Which is why we call this vector AB. Okay, now we're going to make vector BC. Okay, so that's going to start at B and then go up to some point C. I'll make it a little slanted here. so then this is vector BC. So if I were to follow along these two vectors, if I were to start at A and then go to B and then go from B to C, where do I end up? I end up at C. Okay? What this is saying is, instead of doing those two displacements, if I want to end up at C, I can just go directly from A to C. Okay? So that's going to be this vector, which is sometimes called a resultant vector. Okay, so that vector AC comes from the addition of AB and BC. Okay, so AC is equivalent to these two vectors, the sum of those two vectors. Okay, so this just says, in other words, the single displacement represented by the vector AC has the same effect as the other two displacements together. And we call the vector AC the sum Okay, so that's going to be the sum of the vectors AB and BC. And we write AC is equal to AB plus BC. Now there is a special vector called the zero vector, and that is just denoted by a bold 0. That's going to represent no displacements. Okay, so that's a special type. Then, if we're going to find the sum of any two vectors u and v, so if you're finding the sum of any two vectors, you can sketch the vectors equal to u and v with the initial point of one at the terminal point of the other, which is referred to as the head to tail method. So this is, it says you can observe this in figure 1 below. See how this is the terminal point of u, but then it starts at the initial point of v? Okay, that's what this is saying. And like I said, it's traditionally called the head to tail method. For head to tail vectors, because the head of one vector is at the tail of the other one. Okay, and that's helpful when you're figuring out what the sum of those two vectors are. Okay, because this is the sum of the vectors, your u plus v. Now, if you draw u and v starting at the same point, which is definitely going to happen when we start to do our story problems, then u plus v is the vector that is the diagonal of the parallelogram formed by u and v, which you can see in this figure below. Okay, that is going to be something really important as we go into our story problems, so we're actually going to draw another example ourselves, okay, with a different u and v. Okay, and again, yours does not have to look exactly like mine. Okay, but we're going to have some vector, and we're going to call it u. Okay, and then I might have a vector here, and then I call that v. Now remember how I said earlier that vectors can exist anywhere? That means that this vector can exist here, and that's going to form the parallelogram. Okay, so I want you to draw in the diagonal of that parallelogram. Okay, so let's see how our diagonals turned out. If you needed to, you could also put in the V, but you really don't have to in order to find the diagonal. And it's okay if you made it solid. I'm just going to make mine dashed. Okay, but then this should be your U plus V vector. Okay, so see how it's going to make the diagonal of that parallelogram? Okay, so this is, like I said, often called the resultant vector. And then this is something that we're going to use tomorrow. Okay, so the next thing we're going to talk about is the multiplication of vectors. And the multiplication of vectors by a scalar. So if A is a real number and V is a vector, we can define a new vector as A times V as follows. So the vector AV is going to have a magnitude of A times V, and it has the same direction as V if A is greater than 0. Okay, so the same direction as V if A is greater than 0, and the opposite direction if A is less than 0. Okay, if A is equal to 0, then when you do your multiplication, you would get the 0 vector. Okay, and your 0 vector, because it does not have a magnitude, is not going to look like a vector. It'll look like a dot. Okay, because it doesn't have any horizontal or vertical component there. This process is called the multiplication of a vector by a scalar. So if you're multiplying the vector AV by a scalar, it is going to either stretch it or it's going to shrink the vector. So it has the effect of stretching or shrinking the vector. The figure 3 shows the graph, the graph of the vectors for different values of A. And one thing you can notice is that you would write the vector -1 as the opposite of V. Okay, so negative V is the vector with the same length as V, but with the opposite direction. Okay, and we're going to go over that and then we'll come back to this. So this is your given vector. Okay, V is given. This one is 1/2 of V, which I know it's kind of hard to see up here. So this is half of this vector. You can see it in their sizes, right? It is a half of that. So we would say that this is going to shrink. Okay, and it shrinks by a half. Now for 2V, if you look at the original vector, can you guys see how this is physically double your original vector V? So we would say that this would stretch. Okay, and it's by a factor of 2. Now this is negative V, so this was 2V. This is negative V. And then that one is just going in the opposite direction. Okay, this one says -1/3 V, and so this is going to go in the opposite direction. And it's going to shrink. Okay, and it shrinks by 1/3. And then your last one is the opposite direction. And stretches by a factor of 2. Alright, so then the next thing is the difference of the two vectors. U minus V is the same thing as the vector U plus the opposite of V. And then this is going to show you how the diagonal of u minus v is going to be the other diagonal of the parallelogram. So remember on the last page we saw that this was u plus v. Okay, this is going to be u minus v. So even with the one that we drew, okay, the one that would be the u minus v would be this diagonal here. Okay, that would complete that parallelogram. All right, now the next few boxes are definitions and properties. Some of these are going to come naturally to you, so even if I didn't tell you how to do them or that they existed, you would already know that based on your work with the real numbers. We're going to highlight some of the really important stuff, such as the magnitude of a vector. Okay, so remember, the magnitude is the same thing as the length. Okay, the magnitude and the length are one and the same. Your magnitude or length is given by the equation, the absolute value of v is equal to the square root of a squared plus b squared. That should feel familiar. That is just like what we use to find what? It's exactly what we use to find r. Okay, you're going to see some other similarities as we go on today. This is one that you would do naturally. This is just saying if you're adding two vectors, you add the two horizontal components, and then you add the two vertical components. Same thing if you subtract, and then if you multiply, then what you do is you distribute that scalar multiple. Okay, now the next thing that's also going to be important is the horizontal and vertical components. Okay, so we're going to let v be a vector with a magnitude of v and a direction of theta. Okay, magnitude of v, direction of theta. Then you can make the horizontal component by doing v, the magnitude of v times the cosine of theta. So a is the horizontal component. Okay, and b is the vertical component, and that can be formed by doing the magnitude of v times the sine of theta. Okay, now this part is saying how you can express this in terms of I and j, which leads us to this box here. This is just another way that you can rewrite vectors. So if you have a vector AB, that can be written in terms of I and j by putting the A in front of the I and the B in front of the j. Okay, so I'm just going to show you real quick, if you had something like 3, 5, if you were to write it in terms of I and j, you just write 3i plus 5j. Okay, that's all your component form is with I and j. Yeah.
How does that help you?
What do you mean?
Writing an I and J.
It's just a different mode. So it's just a different way to represent the same thing. Okay, and the book kind of goes back and forth between them. I prefer the vector mode, but it is helpful just to know that there's more than one way to represent your vector. Okay, and then this page is also just naturally stuff that you know. This is the commutative property of addition, the associative property of addition. You have the additive inverse. So all of these are going to be intuitive. You have the distributive property. As we go over and start to do operations with vectors, you're going to naturally do those. Okay, which is what we're going to do on the last page. Okay, so what you're going to do is find 2u negative 3v, u plus v, and 3u minus 2v for the given vectors. Okay, so I'm going to do 2u with you, and then I'm sure you could even do that one by yourself, but I'm going to have you do the rest. Okay, so if you're doing 2u, you're just going to distribute the 2. So 4 times 2 is 8, 5 times 2 is 10, so 2u is going to be 8, 10. Okay, in component form. Yes. Yep. Okay, Okay, so then Blake, for negative 3v, what did you get for that?
Maybe 9, negative 12.
Yep. Okay, and then the next one is u plus v. Okay, so Sam, what's u plus v going to be?
Would that just be 1, 9?
Yep. Okay, and then for the last one, when you're doing 3u minus 2v, what I like to do is distribute first. So I'll do the 3 times u, which would be 12, 15. And then I actually distribute the negative with it, so I turn this to a plus. And if I distribute the negative, then I'm going to have 6, negative 8. And then I can go ahead and just add those together. So 12 plus 6 would be 18. And then 15 minus 8 would be 7. And so that would be my final answer. Okay, so if you haven't already finished B, will you finish that for me, please?
But isn't it,
So you don't mix it together?
no. Flash one.
Okay, so Mitch, what'd you get for 2u?
-2, -6.
Good. Okay, and then we have negative 3v. Sarah, what'd you get for that?
6, -6.
Good. Okay, and then we have u plus v. Carmen, what'd you get for that? Good. Okay, and then the last one, the 3u minus 2v. Again, I'm just going to show you how I distribute. So I would have negative 3, negative 9. And then I would add that to 4, negative 4. Which would give me 1, negative 13 when I added those together. Okay, any questions for me on those? Got it? Okay, so then the next thing we're going to do is find different magnitudes. So the first one, the magnitude of u, is going to be the square root of a squared plus b squared. Okay, and if you want to write these in terms of component form, like negative 2, 2, you could do that if you like that notation better. Okay, so the a and the b are the coefficients of I and j. Okay, so this is like negative 2, 2, this is like 1, 1. So if I'm finding the magnitude, and the magnitude is a squared plus b squared, this is going to be negative 2 squared plus 2 squared. Okay, so 4 plus 4, which is going to be the square root of 8, and then simplify. So square root of 8 is going to reduce to 2 root 2. Okay, and now we're going to do v. Okay, so for v, my a and b are 1 and 1, so it's just 1 squared plus 1 squared, which ends up being the square root of 2. Okay, now the next thing we're asked to find is the magnitude of 2u. Okay, so one way that you can do this is you can multiply the 2 by the u first. So if I multiplied negative 2, 2 by 2, I would have negative 4, 4. So when I take the actually, I'm going to write this like this first. Okay, so if I'm just finding 2u first, this is the vector, and then if I'm finding the magnitude of that vector, then I can do the square root of -4 squared, which is 16, and then 4 squared, which is also 16. Is it okay now if I just square that in my head? Okay, so then 16 plus 16, you can either think of it as 32, but 16 plus 16 is just 16 times 2, and the square root of 16 is 4. So this is going to be 4 root 2. Okay, and then if you have 1/2 v, the magnitude, first I'm going to find the vector. Well, if I take half of 1, 1, I'm just going to get 1/2, 1/2. So then when I go to do the magnitude, I'm going to do the square root of, what's 1/2 squared? 1/4. 1/4 plus 1/4 is 1/2, right? The square root of 1/2. So then I can rationalize. I have the square root of 1 over the square root of 2, which is going to end up being root 2 over 2. Okay, now notice what happened here. I found the magnitude of u, and I got 2 root 2. I found the magnitude of 2u, and I got 4 root 2. What's another way I could find this?
Divide the magnitude of u by 2 if it's 1/2 u.
Okay, so yeah, so here you have root 2 and then root 2 over 2. Okay, so for that one you could divide by 1/2. By this one you could do what? Multiply by 2. See how it's multiplied by 2? Okay, so or if this is double, it's just going to be double what your magnitude is of the vector. Same thing with this. If you had root 2 and now you're multiplying that by 1/2, you'd get root 2 over 2. Okay, so see how that's going to be a quicker way to do those? You can just multiply it. Alright, now we have to do u plus v. So the first thing I would do is find out what that vector is. So u plus v, -2 plus 1 is -1, and then 2 plus 1 is going to be 3. So now I can find the magnitude. So -1 squared is 1, 3 squared is 9, which means that's going to be root 10. And then I can do u minus v. Okay, so -2 minus 1 is going to be -3. 2 minus 1 is going to be 1. See how these are the same values? You have a 3 and you have a 1. When you do the magnitude, because you're squaring them, you're going to get the same thing. So -3 squared is 9, 1 squared is 1, so you're going to get root 10. And then do you guys remember from before how we said that u plus v and u minus v are going to form the diagonals of a parallelogram? Do you guys remember what type of parallelogram has congruent diagonals from geometry? Yep, and a rectangle.
Oh yeah.
Okay, so that means that these two together form that shape. Alright, and then the last one that we have to do is the magnitude of u minus the magnitude of v. And so we would find the magnitude separately, but we already did that. So the magnitude of u was 2 root 2. The magnitude of v was just root 2. If they're like terms, you can combine them. How can you tell if a radical is a like term? Yeah, Michaela, you remember? Why? You have to have the same root and the same
Number under.
Yep, radicand. Yep, So see how this is They both have the square root of 2. Okay, so you can just subtract the coefficients. We did this in chapter 1. So 2 minus 1 was 1, so it's just going to be 1 root 2 or root 2. Now you can only combine if they're like terms. So if they were not like terms, you would just have to leave it. If this was root 3, it would be 2 root 2 minus root 3. Okay, so that has to be the same root and radicand. Okay, now this next one, we have to find the horizontal and vertical components with the given length and direction. And then we're going to write the vector in terms of the vectors I and j. So if we look back at our equations, to find the horizontal components, I have to take the magnitude and multiply by the cosine. And then for vertical, I can take the magnitude and multiply it by the sine. Okay, so that's exactly what I'm going to do. So for this one, I can set up my horizontal component, which is A, is going to equal the magnitude times the cosine of theta, while the B is going to be the magnitude times the sine of theta. Well, they already tell us the magnitude is 4, and the cosine is 30 degrees. And this is nice because 30 degrees is on your unit circle, so you can just go ahead and find the exact value. So what is the cosine at 30 degrees? Good. So then your A component would be 2 root 3. And then your sine would be 1/2, which would make that 2. So now you need to write it in terms of I and j. So this would be 2 root 3 I plus 2 j. Okay, because remember it's AI plus BJ. Okay, and for B, this one's a little bit different. And that's because when you do the cosine, is 15 a place on your unit circle? Okay, so then we're going to have to use our calculator to find what that is. And it's really important that you remember to do what? Yep, you have to be in the right mode. Bless you. Okay, so I have to make sure that my mode is in degree. Okay, and I was teaching sine, cosine, and tangent to my geometry people today, so I am in degree. Okay, so then you're going to find your decimal, just correct to the nearest hundredth. Okay, so round to the hundredths place.
Are these formulas that we'll get?
There's going to be a mixture.
Yeah,
Some of them, like, you know, when you're first doing it, it's like, oh, there's so much. But then a lot of the stuff you just do naturally anyway. And we're going to be doing it so much it'll get ingrained in your brain. Okay, and then, Lucas, what'd you get for B?
0.52.
Good. Okay, so then it'd be 1.93I plus 0.52J. Okay, great. Now, the last thing we're going to do is find the direction of the vector and the magnitude. So the magnitude remember, is going to be the square root of a squared plus b squared. To find the direction, we're going to use the tangent of theta. Who would have thought? Exactly what we used before, right? In polar coordinates. Okay, so it is very similar. Okay, so the first thing we're going to do for this one is find the magnitude, which this should go pretty quick. Negative 4 squared is 16, 3 squared is 9, 16 plus 9 is 25, the square root of 25 is 5, so that's going to be your magnitude. Now before, I was telling you how vectors can be anywhere. Once we start dealing with directions, we are going to use your terminal side like we usually would, which means that you're going to have to pay attention to the quadrant. So when you're doing the tangent of 3 over negative 4, you want to find that in the same quadrant as where this point would be. Okay, so negative 4, 3, okay, would point in what direction?
Second quadrant.
In, yes, the second quadrant. Okay, even if it was at a different position, it would still point towards your second quadrant. Okay, so we have to find this in quadrant 2. So when we do the inverse to find our theta, I know I'm not going to get what's in quadrant 2 because remember the inverse automatically gives us either 1 or 4. Okay, so this is given to us, which is in Q4. So to get it in Q2, what should I do to this value? Add 180. Yep, so, before we were adding pi, and so this is equivalent to that. So your theta value would be 143.13 degrees. Okay, and remember it's that adding by 180 that takes your angle from quadrant 4 to quadrant 2 because they're going to be a straight line. Okay, so that's why we're adding the 180. Alright, and then that's all you had to find, so you're done with that one. So for B, we're going to do something similar. Okay, again, if you want, you can always rewrite this. Just don't forget your negatives. So when you're doing the magnitude, you're doing the square root of root 3 squared plus negative 1 squared. Root 3 squared is 3, negative 1 squared is 1, and the square root of 4 would be 2. So that's going to be your magnitude. Okay, so now you guys can finish the video. I'm going to finish it right now. Okay, and you're just going to find your tangent, which is going to be B. Hey, if you guys could be quiet, I told you I'm finishing the video. Okay, so you're going to multiply to rationalize, and you get negative root 3 over 3. Okay, if you are using your calculator, it is going to give you the theta in quadrant 4 as negative 30 degrees. You can keep it like that, or you can also rewrite it as 330 degrees. Okay, by adding 360. All right. Okay, and then your homework is the 11 through 16, 19 through 20, 31 through 35, 37, 38, 41 through 52.